microphone over my ear work? You can all hear me? Right, good. We'll carry on. So I've taken my brief as being, the last on in the day, and it's 28 degrees outside, and it's a Friday evening, so it's just videos and pictures and not very much hard science. Right, so already I've been teed up with the when will we have fusion. So even before I've started and I get asked that question, it's impressive. I steadfastly refuse to answer that question, by the way, because I'm not stupid. But what I would say is that I will ask you the question, how much money are you prepared to spend and how much risk are you prepared to take? And then I'll answer your question of how long until we have fusion. Right, I thought I'd start with what's the whole point of this type talk? Okay, nothing is moving. Where am I pointing this at? Any help? There we go, right. I don't know if that was me or you, anyway. This was some data that NASA released last year. This is global average temperature around the months of all the years since the 1880s. It's spectacularly boring, this data. Nothing happens. For a long, long time, global average temperatures just don't change for about 100 years. And that should really scare you, that nothing happens even though we're pumping a lot of carbon into the atmosphere, burning a lot of coal, and nothing's really happening. We're just layering up insulation, layering up, not really seeing any change. Until about now, until about the 80s, and you can begin to see increases in temperatures, and then you get to the 2000s and it gets a bit more worrying. So the last 20 years have been steady and sizable increases, and this data I think should terrify people. If you look at that over 140 years, as I say, 140 years of burning carbon, nothing happens for 120 of it, and then it goes quite badly wrong. And this shows you the inertia in the system. So there's a huge amount of inertia in the system. It's on a very bad trajectory, but unfortunately there is still a huge amount of inertia in the system. So trying to right it, trying to bring it back, it's not going to happen in a short time because there's that latent inertia in the system. So that should terrify you. Another thing that should terrify you is where we actually get our energy from today. So 2000s, right? So I just showed you 2000s things are starting to go badly wrong. And people know about climate change then. They don't really admit it, but they know about climate change. But since 2000, we now burn about 50% more fossil fuels than we did 23 years ago, which is horrifying, but true. And it's all going in the wrong direction. It's all going north and going north pretty quickly. You all know this data, right? But it's worth looking at occasionally. So stack up the bottom three, the black, orange, and the red. That makes up for just over 80% of the energy that we consume today, and it's getting worse. So we are burning more coal today than we ever have. So it's all going in the wrong direction. And the thing that I think worries me the most is how glib people are about this. I talk to so many policy officials and ministers, and they say, oh yeah, we'll get to net zero by 2050. We're going to get to net zero by 2050. We're not going to get to net zero by 2050. Not a hope in hell's chance of that. And so let's try and put some numbers to it. So if you add up those, the black, the orange, and the red, roughly speaking, what's that? 11 gigatons of oil equivalent. So that's 11,000 megatons of oil that we have to displace, even if demand didn't increase, which obviously it will. But even if demand didn't increase, you've got to get rid of 11,000 megatons of oil in, roughly speaking, 11,000 days. 2050 is not quite 11,000 days away, but that's artistic license. So you've got 11,000 days to get rid of 11,000 megatons of oil, so just one a day would be a good start, right? So you've got to get rid of a megaton of oil a day. What is a megaton of oil? A megaton of oil is like Sizewell, so the biggest nuclear power station in this country, or Hornsea, the biggest offshore wind farm in the world. You've got to build one of them every single day for 30 years, just to displace the fossil fuels that we burn today. We are not even close to doing that, not even close to doing that. Either one of those, in kind of big handfuls, costs about 10 billion. So you've got to spend 10 billion a day for 30 years just to displace what we burn today, let alone what you have to do to grids and networks and storage and all the other stuff. So just for generation. That's roughly speaking about 4% of GDP. We could do that. The world could spend 4% of GDP on clean energy, but we're not even getting close to it, order of magnitude off at the moment. So, this is a huge problem and people are far too glib about it. And this is just data, right? So what the hell do we do about it? I'm going to frame this talk around 3 quotations. The first of which is from someone you know well, and I'd say to policy officials, frankly, you could do worse than take policy advice from Stephen Hawking, who was asked, what do you want to see humanity do? And he said, this is easy. I want to see fusion power, for many good reasons. So what are we doing? We're taking 2 types of hydrogen, deuterium and tritium, heavy hydrogen and very heavy hydrogen. We force them together, and this happens in our sun, it happens in all of our stars, and they fuse. They combine, they produce helium, just inert gas, and neutrons. And the neutrons carry about 4/5 of the energy, and it's a lot of energy. So it releases a lot of energy, the fusion process, incredibly energy dense. So that's what we're trying to do. In many ways, it's a really perfect energy source because it's inherently low carbon. We don't produce any carbon in the process. It's inherently safe if we can make it work and sustain it. Unlike fission, where you can have a runaway, or in a fission reactor, you put fuel in, you've got enough fuel for about a year and a half. So if you have a tsunami or an earthquake or something, it takes a long time to take the rods out, and you've got all that fuel, and you lose control, or you could lose control of it. In fusion, we have inside the machine at any given time about 10 seconds worth of fuel. So if you wanted to stop, really stop. Look, I've spent 20 years of my career trying to keep fusion going. Stopping it is very easy. In principle, it would be reliable in that you don't wait for the wind to blow and the sun to shine. It would just work all the time. It's sustainable in the sense that deuterium we just take from seawater. Actually, I did a calculation recently to work out the equivalent of all the known oil reserves in the world today. If you used fusion, if we could get fusion to work, if you used fusion as an alternative to oil, the amount of seawater you need is 2 cubic kilometers. The UK has 2 cubic kilometers. That's all the oil in the world, right? So it's hugely energy dense. We have plenty of seawater, plenty of deuterium, plenty of lithium on the scale that we need it. And it's incredibly energy dense, the most energy dense thing you can do. So to try and contextualize that, for the rest of my life, even if I burnt electricity like an American, which I don't, but for the rest of my life, all I would need is the water in 1 bathtub and the lithium in 2 laptop batteries. And I own 2 laptops. I could go home and draw a bath. So that's me, raw fuel for the rest of my life. If bathtubs are not a good enough scientific unit for you, how about wheelbarrows? So comparatively, it's a lot of coal. A lot of coal. But there's always a problem, right? So to make fusion happen, I mean, it happens in the sun because of the enormous mass of the sun. So we have this huge gravitational force, forces the light elements close enough to make them fuse because they naturally repel each other. So instead, on Earth, we have to make the fuel about 10 times hotter than the center of the sun, about 150 million degrees, which is even hotter than this room. So obviously, we cannot let that fuel touch the sides of the wall. So instead, we hold the fuel using very large magnets. So here you see some of the biggest magnets that you can conceive, and I'll show you some videos of them later. And they effectively sort of levitate the fuel, keep it away from the wall to stop it interacting with the wall, damaging the wall and breaking the vessel. And that allows us to sustain a fusion reaction. Now, so much, so known. So lots of you knew all of that. But these lights are still not powered by fusion, even though the tokamak came into being in the 70s. We still don't have fusion power. So we have some technical challenges to overcome, and I will talk about 5 key technical challenges and then show you a little bit about what we're doing to address each. The first, and I think the one that people do know, is that the fuel is about 10 times hotter than the center of the sun, which is a real big challenge. And how you both sustain the fuel in a plasma form at that temperature in a quiescent way, and also control it and make sure it doesn't interact with the wall is a really big challenge. This is real footage. This is footage from the inside of jet, and only at that sort of temperature, at 100 million degrees plus, do you get a decent cross-section here between a deuteron, heavy hydrogen, and a triton, very heavy hydrogen. They fuse, they produce alphas, so helium particles, and that's what keeps the fuel hot. So that sort of self-sustains the temperature. And the neutrons. And the neutrons are great in that they're extremely high energy, high flux, high fluence. All of those things are great for producing electricity. Unfortunately, all of those 3 things are awful for the materials that you build the machine from. So the second big challenge is that you have the most intense neutron source on the planet here, and that will cause damage. So these are neutrons streaming through whatever you've built the machine from. It's some structural steel at the back end, probably tungsten or beryllium or moly on the armor. All of those things will see displacements in their lattice, which change their strength, their brittleness, their creep, how long it lasts. And how long it lasts is what affects the cost to the consumer. The third challenge is that, as well as the most intense neutron source, you have incredible heat gradients to deal with. So we talked about the fuel right in the middle is 150 million degrees. The wall, which sits just here, 2 meters away, has to be less than about 2,000 degrees or it melts. And immediately behind the wall, you've got magnets which you've cryogenically cooled to 4 Kelvin. So you've gone from 10 times hotter than the sun to almost absolute zero in 2 meters. So that's quite a big challenge. The fourth challenge is where we get our fuel from. Deuterium, as I said, we just take from seawater. Tritium, very heavy hydrogen, is radioactive, has about a 12-year half-life, so there is no natural tritium. It's all long since gone. So we have to make it, we breed it. This is meant to represent a blanket of lithium, so we put probably enriched lithium around the outside of the machine. As the neutrons stream through that lithium, some will react and produce tritium. You then have to take that solution out into a processing plant, pretty big, complicated chemical processing plant, extract all the forms of hydrogen from the lithium, then separate the forms of hydrogen into protium, deuterium, and tritium, then freeze the tritium, extrude it into ice, chop it up into pellets, and inject the pellets into the machine. And that's put wood on the fire. Keep throwing wood on the fire, it keeps burning. Stop throwing wood on the fire, it just stops. And then the fifth challenge is that we could do all of those things, but if we only ran for 6 months a year, the cost to the consumer would be chronic. So you need very high uptime, very high availability, and we do temporarily make the machine pretty active, right? So you can't send people in. So you need big robots like this that are both dexterous and can do bolts and screw and cut and weld, and at the same time carry high payloads. So those are the types of robotic solutions that we need to deliver. So as you can see, 5 challenges in and of their own right, pretty big things, and then when you integrate all 5 and have to do them all at once, a really, really tricky problem. So what are we doing about it in the UK? Well, we try to address all of those things. So we operate JET, which is the largest fusion device in the world today. It's the best place for studying hot fusion fuel. We have built a machine called Massed Upgrade, which is all about extracting heat from the machine in a reliable way. We have a materials research facility where we can look at irradiated samples, things which have been exposed to high neutron flux, and see how the properties have changed, typically small-scale materials, the types of things actually you would do in Oxford labs, but with irradiated material. And we are building, so that's like kind of micron to centimeter scales we can do there. We are building a facility in Yorkshire where the sample under test, so this bit in the middle, is about me, so it's about 2 meters by a meter, and I am about a meter wide, sadly. And that allows you to look at all the brazes and the welds and the joints and the things typically which fail. And it will be in a 4 Tesla field, so a very large magnetic field, under extreme heat flux in a vacuum, so the combinatorial load that you have in fusion. This facility here we are building at Culham down the road, which will be the largest tritium research facility in the world. We have a very big robotics lab now, looking at robotic solutions, both from, well, I'll show you them later. And we try to stitch the whole thing together with big HPC, big computing codes, which allows us to then design power plants. Right, so what I'm going to talk about today, some of the technical challenges and some of the things we're doing, only videos, and then I'm going to say a little bit about the pathway to actually getting to a power plant. So I'll start with materials. Oh dear, what happened there? Let's try again. So, I don't know, am I pressing this? Are you? Okay, it's working. Well done. So as an example, this is a simulation of pure tungsten. So we put pure tungsten into the machine and then look at how it changes, how it transmutates due to the neutron flux and the presence of helium, and see how the properties change. And as you can see on the graph on the right, what was pure tungsten becomes a pretty horribly mixed alloy. It ends up with quite a lot of rhenium in it, quite a lot of osmium in it, and interestingly, quite a lot of helium in it. And helium is a really bad thing because it causes dislocations and bubbles and all sorts of other things, which are horrible to deal with and fundamentally affect its structure. So as well as being active, it's also less strong. And all of those things are bad. So we really have to care about how the neutrons affect the materials. So to test that, we have built this facility. It's called the Materials Research Facility, where we'll take irradiated samples, which typically come in about this size, finger size, that have been under a neutron flux. We take them through this series of hot cells, chop them up into something which is about fingernail sized, put them into this cask, move them into one of now 24 different research rooms where they're robotically unloaded, put into an instrument for micromechanical testing, where we test things on a micromechanical scale, so micron scale. We are also now building a few hot cells where we can look at the length scale from microns to centimeters, which is quite a few decades. So we can look at how that affects and then be able to, with greater confidence, extrapolate from centimeters to meters. So those are the types of things that we're doing. On tritium, I discussed how we have deuterium and tritium. We fuse them together, they produce neutrons. The neutrons then react with the lithium. Typically, we want quite a lot of lithium-6 here, so high enrichment, which produces a helium and a triton. And then you take that triton out, do the processing, and re-inject it. That is a pretty complicated chemical loop. We, 3 years ago, went about designing and building that facility, which now really exists. This will be the biggest closed-loop tritium research facility in the world. The whole point of it is it's full processing plant. So it goes from storage of the tritium, which we typically do on a metal hydride bed. You heat that up, extract the tritium, extrude it, freeze it, extrude it, inject it into vacuum, combine with other gases, then extract that, and then separate the other gases, which is quite complicated chemical processing. And then particularly difficult is the separation of the isotopes of hydrogen, which whilst actually is not that difficult, it is quite cumbersome. So this column here is a cryodistillation column, which we move the gases up and down and separate the different types of hydrogen into protium, deuterium, and tritium. And that's a 25-meter tall column, so it's a pretty big processing plant. And then at end of life, you also want to capture the tritium, which is embedded in the wall or embedded in the coolants, because A, it's radioactive, and it makes that a higher level of waste, which you don't want to put in the ground. And B, it's your fuel, so you actually want to get it out again. There is nothing else that does this, the full closed loop from storage all the way through back to storage. So it's completely unique, but it is small compared to a power plant. This is about 2% of the scale of a power plant inventory. So we can take about 100 grams, a power plant will have to take a few kilos. So whilst it's an important step, it is only a step. So this is now well under construction. Indeed, the building and the HVAC and a number of the components are now installed, but we will be another couple of years completing all the plumbing before it's activated. This is our robotics lab. It's called RACE. It's a good example of where you have an acronym and then work out what it's going to stand for. So it's remote applications in challenging environments. It's robots where you don't want to send people, basically. It's the subtitle for it. So we do these types of robots, very big boom robots. This is a robot with 7 knuckles that has a 10-meter reach. It can pick up hundreds of kilos, but at the same time, incredibly dexterous. So it's all person in the loop. So you see the person sat 50 feet away from the hands of the robot, all haptically force feedback. What the person does, the robot does. What the robot feels, the person feels. Whilst it can also pick up hundreds of kilos, it's very, very sensitive. So if you ran the finger of the robot along the wall, the user would feel, I don't know, like a piece of sellotape, something on sub-millimeter precision, despite being sat 50 feet away. So incredibly dexterous. It can cut, it can weld, you can feel the biting point of a bolt or a screw as you're doing it up. Incredibly, incredibly flexible system, which has lots of applications outside fusion, by the way. I should have said, that robot, so we have two of them, two big boom robots. Both have an operator team of 40 people. When you get to power plants and you've got hundreds of robots, you can't have 40 people to operate each robot, because then your operations costs are enormous. So you have to be much cleverer about it, and ideally have one control software which all users can operate all robots. Because we will have lots of different types of robots, sort of industrial robots down at the bottom, big boom robots at the top, quadrupeds for sensing down at the bottom, drone robots, telecask robots, all sorts of things that you would like to move autonomously at the top. So what we're developing, as well as working on all of these and the radiation hardness of all of these and the dexterity of all of these, we're also working on a sort of middle layer which sits between the control software of the individual robots and the user, so that the user has one interface to control all of these frankly, very dissimilar robots. And again, that has lots of applications in stuff beyond fusion as well. I talked about our thermohydraulic testing. So we have now built this facility in Yorkshire, which at the heart of it will have a magneto-thermal hydraulic combinatorial load test. So the sample in the middle, this bit here, is about 2 meters high, it's about 1 meter across. Firstly, that goes under extremely high heat flux, so it goes on about 20 megawatts a square meter, which is really, really high heat flux, sort of re-entrant space shuttle type heat flux. So you put the sample under that, and that sample can do obviously all the brazes and the welds and different coolants. You then apply a 4 Tesla field, so a pretty large magnet goes around the outside of it, and you can do ramps up, ramps down, changes in magnetic field. On top of that, we put pulsed magnets, which can then simulate a sort of off-normal thing, where if you get a flux of plasma going in the wrong direction, that creates a flux of magnetic field. So we can look at rapidly changing magnetic fields on top. And then the whole thing is encapsulated in a vacuum with high-pressure coolants. So it looks at all of the loads that you have in fusion apart from the neutrons. Everything else is captured in this. So this, again, is a first of a kind, which does the magnetothermal and hydraulic testing. So we're very excited to turn that on. We're in the assembly phase of that at the moment. It should be complete by the end of next year. And here you can see some pictures of that. So power supplies are now installed. The shielding is pretty much largely installed. We have the highest power continuous wave laser that you can buy commercially, at least. In defense labs you might find higher. But commercially available, highest power continuous wave laser for spot heating parts of the machine. The induction rig is now complete, so lots of it is now ready. Right, so that's all the underpinning technologies that allow you to make progress on some of those technical challenges, but it doesn't answer your question of when are we going to have fusion, right? So let's talk a little bit about the next step and how you move to power plants. Let me first of all say some of the latest results in the field. I'm only going to show you 2 slides on this. So for the first time last year, the National Ignition Facility, which is a US facility, demonstrated, at least in thermal power, that they produced more thermal power, fusion, than the thermal power injected into the capsule. Now actually, to produce that 3 megajoules, they had 300 megajoules at the back end of the laser system, but the lasers actually injected 2 megajoules into the capsule. So 2 megajoules in, 3 megajoules out, so it showed a thermal gain. Also at JET, so this is JET, a facility that we operate. This is the biggest currently operating fusion facility in the world. You'll see a person in coveralls in a minute, which gives you some sense of scale. So here's a normal sized person. It's about 12 meters by 12 meters, give or take. It's a big industrial scale plant. There's nothing else like it. It's the only one that can operate with the amount of tritium that we have, the only one with the same mixture of metals that a power plant might use, the only one with a robotic maintenance system. It's just unique. And last year we broke the world record for fusion energy released, which was about 59 megajoules. Now, that is just about enough to power your electric car from here to Birmingham. So, and it only lasted for 5 seconds. So that is certainly not a power plant. However, it was never designed to do any more than that. That was exactly what we predicted. And that's the important bit. We made a prediction in advance and it did what we predicted. And that prediction is what has designed this machine. This is a machine called ITER. This is the largest scientific collaboration ever undertaken by humanity, so much bigger than CERN, much bigger than the space station. And yes, these are all the partners, and they really are working together. So you really do have China working with the US, and Europe working with Russia. And then these 3 are relatively friendly. So it's a fun project, both technically and geopolitically. The aim of ITER is that you put 50 megawatts in, so thermally, 50 megawatts in, and it produces 500 megawatts out. So that's a big thermal gain. Now, actually, in electrical power, it's still a consumer. But in terms of thermal power, it would be a big gain. And that's the aim of the machine. It's about 80% built now, but it will still be quite a few years until it starts operating, sadly. One of the reasons that it is late and over budget, actually, I should have said scale. So this is about 80 meters here. It's about 120 meters long. It's about 80 meters out the ground. So one of my bad jokes is that this is like Wembley. It's the same amount of steel as Wembley. It's more or less the same dimensions as Wembley. And like Wembley, it's about twice over budget and twice behind schedule. But it is more complicated than Wembley. And one of the reasons that it's complicated is the geopolitics. So I talked about these big magnets that hold the fuel at the start. In ITER, there are 18 big magnets. If you were running a sensible engineering project, you would say, right, I've got 18 of these first-of-a-kind complicated magnets. I tender to the market and say, let me find a magnet engineering company that can build me 18 magnets on the same rig to the same spec. Absolutely not how ITER works. Because imagine I'm the US Department of Energy, I've invested in ITER, and the contracting company to build the magnets is a Chinese company. That would never happen, right? Because then the US are then reliant on China to build their power plants that follow. So it was never going to work that way. So instead, you've got 18 magnets, 3 each being delivered by a different partner. And then the quality control for that is like hell on earth, because they're all in different bits of the world, but they have to be, to millimeter precision, the same. right? So this is really difficult. And the construction of those 18 magnets is 10 times more superconducting strand than the world had ever made in one project, right? So it's a huge engineering challenge. Just jacketing the strand requires things like this. This is an 800-meter long jacketing bench in Florida, which has to be aligned to centimeter precision across 800 meters. So it's an incredibly complicated piece of civil engineering. And because it's ITER, you're not building one, you're building lots. And so here's one in China, right? So the same thing, just repeated in China. Now that's a really good thing for projects that follow, because you're building a global supply chain and you're building lots of suppliers that are capable of this. But for the one project, it's an absolute frigging nightmare because they have to pay for 6 of these. And then once you've built that jacketing bench and you've built all the strand and you've supplied all of that and you've sent it to the magnet manufacturer and the magnet manufacturer has wound it and insulated it, you then have to impregnate that coil to make sure that all the windings are insulated from one another. And the coil itself is about 25 meters, so it needs a very big oven to go in. And that very big oven is a very large civil engineering project in its own right. So you have to build an oven, which is 48 meters by 20 meters by 5 meters, and heats perfectly isothermically. So that's a big challenge, but because it's ITER, you're not doing it once, you're doing it lots of times, right? So now you can see why it might be a bit late and why it might be a bit over budget, because it is bloody complicated. So having built those magnets, this is the state of the site. Actually, this video is about a year old now, so it's a little bit out of date, but it gives you some sense of scale. So over here is a 4-hectare switchyard, the largest AC/DC distribution center in Europe, the largest cryogenics plant in the world. It's a phenomenal piece of engineering. It's about Hinkley Point, so you will have seen videos and pictures of Hinkley Point. More or less the same footprint, more or less the same scale, much greater complexity, actually. So the technical challenges of ITER are enormous. The magnets is a good example where 10 years ago when we tendered to build those magnets, and this genuinely happened, the tender went out, the largest magnets manufacturing company in the world replied and said, have you put the decimal place in the wrong point? Right? So they were asking for totally ridiculous things that nobody had ever done. Look at the scale of some of the bits of engineering. I'll show you just 2. So these are the vacuum vessel segments. When the machine is built, it's built in like segments of an orange. There are 9 of them. They are 60 meter circumference, so like nuclear submarine, they have to be welded to 2.5 millimeter precision. Under a nuclear code and standard, under high pressure vessel regulations. It's phenomenal engineering. That has been done to 1.5 millimeter precision. So it has been done. Those first components have been installed in the pit. There are non-conformances, by the way, on some of those sectors, and so they will have to have some remedial work to them. This bit down here is one of the segments of the magnet that goes down the middle. That magnet, which comes in 7 segments and gets built up, 4 of them are now on site, that magnet produces a magnetic impulse equivalent to the weight of an aircraft carrier. Let's get your head around that. So you put a magnet over an aircraft carrier, lift it out of the ocean. It's just crazy, crazy engineering, right? So it's all bonkers, it's all mad. And a phenomenal project to be involved in, both for the complexity of the engineering, which is great fun, as well as being crazy, also for the geopolitics, because it gives me some confidence in humanity. I mean, this is a really tough problem, and all those countries really are working together and all really reliant on one another, which is it's actually enthusing about the world. But it is all too big and all too expensive, which leads me to my second quotation from Walter Marshall, who's a prescient guy, who said, there will come a time that we sustain a fusion reaction. Yep, tick, done that. Then there'll come a time that we get as much energy out as we've put in. Well, we can contend thermally we have done that. However, there'll never come a time when you get as much money out as we've put in. And this really matters. The community don't think enough about this. I think this is, every person that joins my organization, I insist that they know about this quotation because it is really important. Let me give you one example of that. I'm slightly talking shop, but I went to a design review 6 years ago with all the European countries. They'd all tried different ways of extracting heat. So the thing that gets all the heat at the bottom, they tried different ways of manufacturing that component. All really complicated, phenomenal bits of engineering. They'd put in high heat flux reactors and high heat flux test facilities. They'd done 20 megawatts a square meter, which is really, really hard to do, for thousands of cycles, and they all worked. And there were 7 different countries saying, well, this is great. We're going to take forward all of these designs. And so I put my hand up and said, how much did they all cost? And nobody could answer the question. Nobody had any idea how much they cost. So I said, well, why don't we find out how much they cost and take forward the ones that were the cheapest, if they've all passed spec? So they went away and found out how much they all cost. They worked out, the full manufacturing cycle and the full life cycle costs of those things. And the cheapest one was 2,000 times cheaper than the most expensive. But the community wanted to take them all forward. So that shows you we're a research community, right? We're not set up to drive the commercialization of that, which is why I think this is so important. ITER, that big project, I'm personally, knowing what I do about the field, I'm convinced it will actually work eventually. It's really hard, but I do think it will get a big thermal gain and it will show that you get more power out than you put in. But top to bottom, it's going to cost well in excess of 20 billion. I don't know how much in excess, but well in excess of 20 billion. It's going to be at least a decade late, and it's only going to produce 500 megawatts of thermal power. That is not a way to a commercial product. Nobody will buy that product. If fusion machines have to look like that, fusion will never enter the market. It's all too big, it's all too expensive, it's all too slow. So Marshall would be right. There is no way that we can commercialize fusion based on that product. Now, much cleverer people that came before me realized that. So whilst we are supportive of ITER, and we do think it's been enormously important in setting up a supply chain and developing capability, if power plants look like that, they won't ever get built. So we have to have another way of designing power plants. Now, one of the main reasons that ITER is so expensive is because it's a sort of conventional ring donut shape, right? And I just talked about those enormous magnets which fit more or less down the middle. So you produce this enormous magnetic field, more or less down the middle. The fuel is out here and feels less than half of the magnetic field that you just spent billions of dollars on. So you really do, of that 20 billion of ITER, a third of it is magnets and cryogenics to cool magnets, and a third of it is very big buildings, big nuclear concrete buildings. So that's where all the money goes, is in the magnetic cage. And you're using actually less than half of the magnetic field that you've paid for. It's not hugely efficient. So rather than having this ring donut, let's just squeeze it in, push it very close to the magnet so that you need lower magnetic field to produce the same power. So that's the genesis, the notion of the so-called spherical tokamak. So instead of ring donut, you squeeze it in. It looks kind of spherical from the outside, although topologically it is still toroidal. And that strips out billions of costs from magnets and buildings to put magnets in. So that's the idea. And it's a great idea. We built the first one of these in the 90s, showed that it was far more efficient than the conventional way. But nothing's ever free, right? If you take something which is hotter than the sun, and you put it into a smaller box, the chances of melting the walls of the box are obviously a lot higher. So you have a really, really, really difficult heat exhaust challenge. So everybody else in the world, really pretty much every other country, although the US sort of in this program, everybody else said the spherical tokamak's a nice idea, but you're going to melt the wall. You don't have a way of building a power plant on that. It will just melt. And so nobody else really invested in it. The UK have always been a proponent of this, and we sort of raged against that and said, we agree, it will melt, we have to find a better way of exhausting the heat. So we convinced the government to build this machine, which is a machine called Mast Upgrade. It won the Royal Academy of Engineering's Major Projects Award in 2021. I'm very proud of that. First time, by the way, a public project has ever won that award. It usually goes to very big gas plants or very big bridges and things like that. It's the first time a public project's ever won it, frankly, because it is the most complicated piece of engineering the country did in that year. The whole point of this project is that we're trying to reduce the heat which gets to the wall. Now, the bit in the middle here, which is hotter than the sun, you're putting a huge amount of energy into something which is really thin. The plasma is about 100 times thinner than air, and lo and behold, it undergoes some turbulence. So some of the hot stuff gets out to the edge. We use magnets to sweep it down to a sacrificial surface down at the bottom. Now, if you built a compact power plant like that, that sacrificial surface would melt after a few months. So it's not a way to regularly running. So what we've done in the upgrade is instead of hitting the surface here, we sweep the plasma out to a surface out here. Now that's only in real estate 50 centimeters. So it doesn't take up a lot of room and it doesn't cost a lot of money. But in 3 dimensions, because it's still topologically toroidal, those particles are going around and around and around. And that 50 centimeters is actually to the wall and back again. So it's 20 meters path that those particles move along. And that whole 20-meter path, they'll radiate their energy, they'll cool down, You can also fill this box down here with deuterium and argon and krypton, all sorts of muck. And that means that when the particles come in, they'll undergo all sorts of charge exchange losses and various other losses, which spread the heat over the full wall rather than depositing it all in one localized sort of spot heater. So that was the thesis. We then computationally worked out what we thought this would do in terms of the heat flux density, which is this red line, of a conventional design, how ITER's designed, how JET has always worked, which so is normalized to 1, has a very high heat density in a very narrow region. So it's only a few centimeters, all the heat goes into one region. So that's how every other fusion device works. And we said, with our new design, don't worry about the nomenclature, but the blue line is our new design, we think we can drop the heat density by 10 times, more than 10 times actually. So we published that in open literature 10 years ago, and any good scientists know that that is the really brave thing to do, to say 10 years before you know you could get a result, this is what we think is going to happen. And then we built the machine at significant cost, both to our health and to the exchequer. And we turned it on a year and a half ago, and these are the first results. And if you want to see experiment match modeling, you could do worse, right? You really could do worse. So this tells me two things. One, that we do have, at least in some way, a predictive capability. And secondly, that it works. It really does reduce the heat. In fact, we are now about 25 times better than any other group in the world has done. And this is a major advantage. If you can say, in any discipline, I'm 25 times better than my competitors, you have a big market advantage. So this is transformative in our field. And it really does open the pathway to, instead of these giant plants, to having a small plant and not melting the walls. So it's a really, really, really important result. And it's all UK IP, by the way. So the UK government are investing in a power plant design program where we actually take that thesis and we try and build a prototype power plant which produces net electricity. So it will not be reliable, it will not be cost competitive, it will need huge subsidy, it won't work most of the time, so it's not a real commercial plant, but frankly nothing that's ever entered the energy market has been. It's always required subsidy and it always takes a long time. So the aim is that it produces net electricity. Most importantly, it's lower capital cost. If I take China as an example, so I talked about how China involved in ITER. The Chinese market is enormous, absolutely enormous. They're involved in ITER, they have paid 9% stake. So they're 9% members, they have access to 100% of the IP. So they're going to they're very overt about this, they'll take the ITER design and they will build it many, many times. And that will drive down price over decades through volume. So that's their approach. The UK is just not big enough. We're not big enough as a government to build 10 plants on the balance sheet of the exchequer just to drive down price. We also don't have the demand, right? So it just doesn't make sense for us to do that. So we have to have a lower capital cost design where it becomes more like gas plant and less than 20 billion. And so the government are invested in this. They've now put, it's actually about 300 million, this is slightly old, this slide, into the concept design phase. This is a kind of big handfuls, what we're trying to achieve. So we're in this concept design phase until next spring. We had to do 4 things. We had to mature the concept. We had to, what we call program development here. That really means we had to set up a site, we had to set up a regulatory framework, and we had to set up a company to do this. As I said before, we're a research lab. We're not going to deliver big infrastructure. So, so we're well in the throes of that. Then we go into the detailed engineering design, where really the pipe goes here, and then get a license. We, in parallel, do some of the long lead procurements and the site development, aiming to do most of the construction over about the 30s, over about a decade, and aiming to begin commissioning in around 2040. Now, that timeline is simultaneously outrageously audacious and depressingly slow. So it is both of those things at once. But it is a huge leap of faith, but we have made big leaps of faith before. When we built JET, so we built JET in the late 70s, early 80s, the reason JET happened was because the oil price was through the roof. And the government at the time was saying, oh my God, the oil price is killing everybody. It's just dominating. It's what the election was going to be fought over. It was the thing on everybody's mind. They needed to do projects which were alternatives to oil. And so the investment in fusion in the late 70s, early 80s was very high. At the time, they spent about 0.01% of UK GDP. So that is not 4% that I advocated earlier, but it's only one project. And we went from this thing, which would have fit on this stage, which was the state of the art in Princeton to this in one step. No computer codes, no simulations, just went for it. So it's a massive step into the unknown. And that's basically what we're trying to do here. So we're going from our little machine that I showed you that got those exciting results on exhaust to something which is actually about this scale, more or less the same 1 meter to 3 meters in radial dimensions. So that across ways, that's sort of 4 meters to 15 meters, give or take, across the machine. We think it'll cost something like 0.05% of the UK GDP, although I did quote that GDP in 2020 and the government are doing very well to send it in the wrong direction, so it might be a bit more by now. How are we doing on those 4 things? So the concept design is well on track. We've actually just gone through an independent review of that. On the regulation, we've long since been advocates that you cannot regulate fusion under the same regulatory framework as fission. It makes no sense to do so. The radiological hazard is completely different. There is no risk of a runaway. There's no risk of a chain reaction. So don't regulate it like fission. It just doesn't make sense to do so. 4 years ago, the government started listening to that and said they tasked a body called the Regulatory Horizons Council, who exist expressly to look at new things that are unregulated. So they've done a study in genomics, they've done one on drones, they're doing one at the moment on AI, so things new to market and how to regulate them, and they did one on fusion. And they suggested that you should have a bespoke, proportionate regulatory framework. That led to a green paper, so a consultation paper by the government, where the government put forward a thesis, then a white paper, and it is now going through the House of Commons as primary legislation. It's been read twice in the Commons, twice in the Lords, and gone through committee. So we do expect it to pass before the summer recess to say that fusion in this country will not be regulated by the Office for Nuclear Regulation. It will be regulated by the Environment Agency, who regulate ionising radiation in hospitals, gas plants, that sort of stuff. So they will regulate fusion. We had to choose a site. We ran a complete volunteer process. We had 15 nominations, which were really all over the UK, shortlisted 5, selected 1, and this is that site. It is, until the end of March, it was a coal power station operated by EDF. It has now closed, so we take ownership of it now. You can see the coal plant, the thermal plant up this end, so this is the coal yard. That is all being put on trains and sent to other coal power stations. The cooling towers and the thermal plant here will come down. There is now a demolition contract in place for that. The substation to the national grid will stay. That's one of the attractions of the site, as is the railway, as is the abstraction license for 2 gigawatts worth of cooling water from the river. So lots of things that you need for a power plant are there. It also has a community that are used to energy plants and want to work on this. So that's really very positive. By the way, the UK government don't go out of their way to buy 350 hectares of land unless they're serious about doing something. So I think this is a real sign that they're serious about fusion. Here, this looks like virgin land that we can just get on with. It unfortunately is not quite that. Underneath this grass is 6.5 million tons of pulverized flue ash. So this is all spent coal, basically, here. This grade here, this bit here, is British coal, and it's high grade, high quality. You can reuse that for cement production. Then we go into slightly less good Polish and Russian coal, which we can use at least for concrete blocks, breeze blocks. And then this end is some pretty awful South African coal, which is not much use to anyone, but we will try to use at least for bunding for the river and roads and civil things like that. So we will try to use as much of that as possible, reuse it in a sustainable way. So that's the site. We are getting on with a delivery partnership. As I've said now 3 times, we're a research body, we don't build plants. And so we need a big engineering partner and a big construction partner to come alongside us. So we are about to, in August, tender, and it'll probably take a year and a half to agree this, because we'll be looking for long-term strategic partners for 20 years to work with us on the engineering and the construction of the plant. So that's another really big step the government are about to take. And I'm expecting that we will get bids from big energy companies, big engineering companies, big manufacturing companies in this, and probably working as consortia. And then the last thing you need is some money. And Treasury are being extremely supportive, and they realise that all the risk at this stage they have to bear. It's too much risk for a company to start investing on the billions of scale for something which is frankly so risky and unknown and never been done before. However, there is increasing market appetite from the private sector for investment in fusion. This shows you fusion companies born over the last 30 years. There were a trickle of them to start with. In the last few years, more and more of them. There are about 50 fusion companies now, so this is not completely comprehensive. Interestingly, of those 50, nearly a third were either born or currently have moved to the UK, which is utterly disproportionate for the size of the country. For instance, General Fusion is a Canadian company, moved pretty much lock, stock and barrel to the UK. Tri-Alpha is a company based in San Diego. They have just acquired 2 companies in the West Midlands. So they're moving significantly to the UK. So Kyoto Fusioneering, Japanese company, have now a big outfit in Reading. So more and more companies moving to the UK, which is a very positive sign, and a proper ecosystem is forming around the country, which is great. The other thing to say is that if you go back only sort of 5 years, really most of the money came from philanthropists, angel investors, very early stage venture capitalists who were putting in tens of millions here and there and taking a bit of a punt. In the last 5 years, we've seen a complete change where we're now seeing sovereign wealth funds, much more patient venture capital money, even some pension funds, remarkably, and most interestingly to me, 6 oil and gas majors have now invested in fusion companies. And they don't do that for no reason. So they are really paying attention. And I will finish with my final quote, which is from Lev Artsimovich. So to answer your question at the start, he was asked in the 1970s in a press conference. He was one of the forefathers of the tokamak. He was asked, when will we have fusion? And he said, I think very accurately, in 1970, fusion will be ready when society needs it. And I still believe that holds today. When society realizes that climate change is an existential thing, and we need to take more risk, and we need to invest much more in low carbon solutions, then fusion will happen much quicker. Thank you very much. I'm very happy to take some questions.
Well, thank you, Ian. Are there any questions? Go ahead.
Yeah, there's a whole load of things in there. So let me just try and unpick. So firstly, I don't think it would be really cheap, by the way, ever, because the plant is really costly. So whilst it might get to being competitive, I don't think it will be cheap. Secondly, on applicability everywhere. So I genuinely do believe that one of the attractive things about fusion is that it works in all jurisdictions. All jurisdictions have access to the water that we need on the scale that we do, to the raw materials, as I said, really, really energy dense. So it can work anywhere. And whilst not every jurisdiction probably has the engineering base to build it, not every jurisdiction has the engineering base to build a gas plant, but every country can have a gas plant, right? Because there will always be a vendor that will go and build it there. So I do think it's available to every country. And the regulation can be much easier than fission, which is one of the impediments to fission rollout. Then on lasers, so I've talked exclusively about not just magnetic confinement, but tokamak magnetic confinement. There are lots of approaches to fusion. I showed you those 50 companies. Those 50 companies are probably pursuing 30 different approaches. So there's a lot of different ways that you can try to do fusion. And one of the things that is being tried, and I did show you very briefly the results from the Livermore lab in the US last year, which is the impingement of a lot of lasers. They have 192 lasers impinged on a tiny capsule, which is about fingernail size. Actually, they don't impinge directly. They go into the walls, and then the walls produce X-rays, and the X-rays collapse the fuel to extremely high density. So what I've described is very low density, about 100 times thinner than air, high temperature, and lasts for a long time. So that's kind of the furnace approach. The laser approach is more like pistons in a car approach, where it lasts for a short amount of time, but you do it at high frequency. Now, there are lots of things to like about that approach. It's much easier from a wall protection perspective, from the longevity of the materials. Probably the tritium breeding is easier because you can have a very large curtain of lithium around the outside. So there are lots of nice things about that. There are different engineering challenges, and you could have a whole nother talk on the engineering challenges of high rep rate lasers and the fabrication of the capsules, which currently cost £10,000 and need to cost 10p. And so things like that, there are different engineering challenges to that approach. Neither is right nor wrong. I just happen to focus on tokamaks today.
I'm told the microphone found a question in the middle of the room.
John.
Go ahead.
One of the things that one must do with a tokamak is to switch it on.
To switch it on,
yeah. And I was looking into a book on magnetohydrodynamics by Molotov and two others. Now, admittedly, they were talking about a completely different geometry. They were talking about a so-called theta pinch, in which the plasma would be confined by magnetic field, which simply consists of straight lines. However, although they discussed this different diagram, different geometry, different device, they drew, you can see a diagram of the electric field just before breakdown, just before the plasma is produced. Yep. And it really is quite a complicated one. It does not only have a component due to the fact that there's a magnetic field changing, so one of Maxwell's equations steps in, but the electric field also consists of, at certain points, strong electrostatic fields due to charges sitting on the walls of the machine. Now, admittedly that work, and it's some years ago, it was for a completely different machine. But I mean, my question is, has an analogous calculation been done by anyone in considering a tokamak?
Yes, is the short answer to that. And you're entirely right, breakdown is complicated. And you do need to care very carefully about the nulls and exactly where you drive your electric currents and how you stimulate the current. But yes, we have lots of different breakdown techniques which we use routinely in tokamaks. Spherical tokamaks are harder than a conventional tokamak. You have a smaller solenoid, less flux swing in the solenoid. It's harder to create the null, but we do have recipes for doing that. And there are lots of different ways. You can do a sort of coaxial helicity injection. You can form plasma rings around the coils at the top and merge them together. You can use some solenoid flux to generate the current. So there are lots of ways of generating a breakdown. And it's a bit hammer. You have to sort of force it. It doesn't naturally want to happen. But yes, we do know how to do that. Yeah.
Thank you. Looking at your slide at the end and discussing the alternative approaches to fusion, I'm reminded of the cold fusion period in 1989 when the UKAEA played a major role in testing the science and ultimately proving that it wasn't viable.
Yep.
Now that there are 3 alternative approaches being tested alongside so-called conventional fusion at the Culham site, does UKAEA have a role examining the science and the technology for those alternative approaches?
We do. Indeed, of at least 2 of those approaches, we have done independent verification of their results. So when First Light Fusion last year showed that they had generated a sort of projectile-based implosion which produced fusion, we put some of our neutron diagnostics and some of our other sensors onto their equipment and verified their results. So yes, we do have a role in being an honest broker and showing that there is technical progress being made in these companies. We have a collaboration agreement with Tokamak Energy, and we are jointly working on some of their experiments as well. So yes, we do that.
Up front here. To your left, microphone's coming.
Thank you for the very interesting presentation. Just wondering, on the supply chain side of the raw materials, are there any constraints in terms of the access to or the availability of those, including lithium, which is also part of driving the electric revolution as well? So servicing more demand.
Yeah. So there are many constraints. The biggest one is tritium, by the way. So the raw fuel, there are, other than weapons application, there's about 30 kilos of tritium in the world available to fusion. 30 kilos, that's all. In a working power plant, you burn about 1 kilo of tritium a day. So your inventory will be gone in a month, unless you make your own tritium. So that's why breeding is so important. But even to start breeding, you need a charge. So that 30 kilos is probably enough for about 10 initial machines to start. And those 10 initial machines have then got to provide the charge for the next 10 to start. So tritium is the most rare and complicated of our supply chain issues. But you're right, lithium is a big issue. Lithium, in terms of raw material quantity, is not that big a deal. To try to quantify that, I did a projection of, let's say, that by 2100, let's say fusion, the first plant is maybe 2050. By 2100, at the growth rate of offshore wind or fission, fusion might account for about 25% of global demand. That's with a really trailing wind, everything working really well, you might be 25% of global demand by the end of the century. Then we would use about 10% of the world's lithium demand. So it's not huge, right? So we're not big compared to lots of other things. The problem with lithium for us is that when you dig lithium out of the ground, it comes about 93% lithium-7 and 7% lithium-6, just raw material. Lithium-6 is much better for breeding tritium than lithium-7. So we actually want to take that 93.7 and turn it into something like 4060. So we want to enrich the lithium so that it's primarily lithium-6. There is no extant supply chain for doing that because nobody else needs to, frankly. So there is no supply base for doing that. So we have to, first of all, convince enrichment companies that they should be working on that, and then they have to scale it. And that doesn't exist today. So that's one of actually many. We have many different rare earths. I mean, the magnets have got various rare earth metals in them as well. So yes, you're right to point out that it's an issue. I don't think it's as big a geopolitical issue as it will be for other industries because actually our volume demand is not very big. The complication for us is the fabrication competence rather than the volume.
Okay, we have a question from the balcony. You have to speak loud.
No, I'm just trying to be truthful. So let me describe the sort of 3 generations. Jet today has copper coils. Those copper coils are hugely inefficient with electricity. They get very hot and they suck a lot of electricity. So we run Jet. When I talked about those great results, which are the world record, we produced about 10 megawatts of fusion power. We put, roughly speaking, 25 megawatts of thermal power into the machine, but we drew about 1,000 megawatts, a gigawatt, of electricity off the grid. So we took a gigawatt off, we produced 10 megawatts of thermal, which would have been about 1 megawatt electric, right? So 1,000 to 1, not great. ITER has about 600 off the plug, that then produces about 50 heating power, which produces 500 fusion power, which is going in the right direction, but that 500 would probably be about 100 electric. So you've taken 600, produced 100. So ITER is also not net electric. STEP, when we get to power plants, would probably still draw about 600. So there's kind of a big recirculating demand. So you have to draw 600 off. You might inject 100 thermal, but you produce 1.5 gigawatts, so 1,500 thermal, and that produces then maybe 800 electric or something. So you're net electric by 200. So you've produced net electric, but only when you get to that point. So ITER won't produce net electric. So we're talking about a thermal gain, but an electrical consumption in ITER, and then STEP will be a big thermal gain and a little electrical gain. Is that clearer?
We have time for one more question because I want to leave some time at the end for Lord Avery to have some closing comments. Yes, go ahead. Why don't you wait for the microphone to come around?
Okay.
We'll do two questions.
Okay, very quickly then. Nuclear forms an important part of our energy mix, but I understand it works best under constant and stable baseload, yet other zero carbon generation tends to be more variable, wind or solar. So will this newer fusion technology be able to provide a more agile output response, or is constant load demand still best?
Yeah, so it's a great question about how things work in a portfolio. The thing that I hate the most about working in the energy industry is this nonsense with different technologies saying my technology is better than your technology. It's just nonsense. We should invest in all of it as quickly as possible, because effectively we're all competing with coal. That's what we should be doing, and not competing with one another. It's just stupid. My view on where fusion enters, so fusion actually, in principle, is extremely flexible in that it could be baseload electric, but actually if you don't have a really high renewable fraction, you might not need baseload, you might want load following. And so one of the advantages of fusion, and actually how I personally think fusion will enter the market, is not for electric, but for heat. Because the really hard to abate stuff requires high-grade heat, cement, ammonia, nitrogen, fertilizers, all that stuff, glass, concrete. It requires high-grade heat that renewables just can't provide, or can only provide really inefficiently. You turn electricity into hydrogen and then burn it. It's really inefficient. So I do think that one of our challenges that I talked about is we have too much bloody heat. We can run the walls really hot, hotter than anything else, right? So we can produce extremely high-grade heat that's then used for industrial processes rather than electricity production. And in a really ideal world, you could be a deliberately cogeneration plant where you load follow and say, right now it's windy, so we'll produce ammonia. And then the wind stops, and so we'll produce electricity. So it could even load follow. So it actually has really enormous potential, but that's all kind of next of a kind before we get into that, I'm afraid.
Okay, one last question, the third row over here.
It was just a quick question about the magnets. You mentioned ITERs using niobium tin, which is a nightmare.
Yep.
Some of the smaller companies are looking at high TC superconductors. Is STEP going to be high TC?
Yes, is the short answer to that. Yep. But not, so some of the small companies are advocating for so they really want to go to the highest magnetic field possible. We want to use high TC actually just because it's higher temperature and a bit easier to do. We're not trying to push to 25 Tesla or something. So we're not trying to go to the highest magnetic field, because you don't actually need to in a spherical tokamak. There are other benefits to HTS that we want.
Okay, let's thank Dr. Chapman again for a really fascinating talk.